Hey everybody, in today's lesson we're going to investigate how lines in 3-space can interact with each other. So let's get started. There are actually 4 possibilities. If you think back to your grade 10 math course, when you guys were looking at intersections of lines in R2 or 2-space, there were 3 possibilities. Either the lines were parallel and they weren't the same line, so they never met, or they were parallel and they were the same line, so they meet everywhere, or they were not parallel, and so 2 non-parallel lines in R2 were guaranteed to meet. In R3, there's actually 4 possibilities. The first 3 kind of mirror what you guys learned in your grade 10 math course. So case 1 is that the 2 lines meet at a single, I'll just say a single POI, point of intersection. So you have 2 lines just going off in their own directions in R3, but they happen to meet at a single spot. Call that L1, call that L2. So that's case 1. Case 2 is you have 2 parallel lines, L1, L2, and 2 parallel lines are never going to meet. They aren't the same line. So we'll say the 2 lines are parallel and distinct. Meaning they're their own line, and they'll never meet. So far, nothing crazy new. Case 3, this third case. So the third case is actually, you have the 2 lines, but they actually wind up being the same line. So just for this visual, I'm just going to switch to a different color and try to do my best here. Say that. That's okay. So we've seen that, a line in R2 can have many different forms, and often the same line can have 2 different equations that look very different. And that might happen sometimes where you have 2 lines, but they wind up being the same line, even though their equations look really different. And so here we'll say the 2 lines are coincident. Which means they meet everywhere, like everywhere is a point of intersection. Okay, so those 3 cases actually mirror exactly what you learned in grade 10. But in R3, there's a 4th case. The 4th case is this, where you have a line. So you have 2 lines that aren't parallel, kind of like what we drew earlier, except they don't intersect. Maybe one passes over the other or one passes under the other. So I'm going to just draw a little dashed line like that to kind of hopefully illustrate that in this case, they don't meet. So this couldn't happen in R2. In R2, 2 non-parallel lines had to meet, but in R3, they don't. They could kind of pass underneath each other. So the 2 lines aren't parallel and never meet. And we give these kinds of lines a special name. We call these skew lines. So that's our 4th case. And what we want to do today is look at what happens mathematically when you try to solve for a point of intersection, and we'll say there is one, or what happens when there isn't one. What happens when they're the same line? What happens when they're skew lines? What plays out? So we're going to do 3 examples here. So here we have 2 lines. So when you're looking at intersection of 2 lines, you want to have in your equations, you want to make sure you're using different parameters. So we have t for our first line and s for our second line. Our key idea for finding the point of intersection, this is by no means the only way to do this, but we're going to set the parametric equations equal. Then we're going to find values of S and T. That satisfy all three equations. So let's see how that looks. So I'm going to do my setup over here and try to conserve my space. Okay, so here we go. So I'm just going to turn these into parametric equations and set them equal all in one step. So if I look at my x components for line 1, I have 2 plus 3t. And if if I'm looking for a point of intersection, I'm going to set those two lines basically equal to each other. And I'm going to match up with the x component of the second one. So if there's a point of intersection, those x value, we're looking for where the x values are equal. So 2 plus 3t equals 3 plus 2s. And then 2 plus 4t equals -1 plus 7s. And then finally, 1 plus 5t equals 2 plus 4s. And then I like to rewrite those in terms of just like the way we normally look at a linear system. So I'm going to write that one as -2s plus 3t equals 1. I'll call that equation 1. So I'll get my s's and t's on either side. What makes the most sense here? I'm going to move everything here to the right. So then I would have 7s, and I'd have -4t. I'm just doing that just to minimize all the negatives I have. And then if I move -1 to the left, I get 3. And then for the next one, I don't think it matters too much. -4s plus 5t, and then 2 minus 1 equals 1. So if I can find values for s and t that satisfy all three equations, then I have a point of intersection. See, the problem is, if I have two equations, two unknowns, I'm going to get one solution. But with with three equations and two unknowns, like there's no guarantee that the s and t I find, solving a pair of those equations will work in the next one. So we have to check to see if that's true. So we got to pick a pair of these that seems pretty easy to solve. So I'm just going to write a little note like this: solve 1/3. So I'm going to look at equations 1 and 3. I'm going to solve that linear system and then see if my numbers work in equation 2. I chose 1 and 3 because I can see if I multiply equation 1 by 2, I get -4s plus 6t equals 2. I'll call that equation 4. Because then I can subtract those two equations, right? If I do equation 4 minus equation 3, the s's go away. 6 minus 5, that's 1t. 2 minus 1 is 1, and I get t equals 1. Let's continue. So I'm going to sub that into equation 1, I guess. -2s plus 3 times 1 equals 1. -2s equals, so I'll have 1 take away 3, -2. Means s equals 1 as well. So t equals 1 and s equals 1 satisfies equation 1 and 3, but does it satisfy equation 2? So we have to finally check in 2 because we solved the system 1 and 3. There's no guarantee that these will work in 2. We got to check. So 7 times 1 minus 4 times 1 equal 3. Yeah, that gives you 7 minus 4. Yeah, 3 equals 3 last time I checked. It actually works in the second pair of equations too. So s equals 1 and t equals 1 satisfies all these equations. This s and t correspond to our point of intersection. We can say the two lines meet when s equals 1 or t equals 1. And we want to ask, well, what point is that? Well, plug in whatever plug it into either one of those equations. So let's do the first one. We get 2, 2, 1 plus 1 times 3, 4, 5. And we get 5, 6, 6. The POI is 5, 6, 6. And if you plug that into the second equation as well, 3 plus 2 is 5, negative 1 plus 7 is 6, 2 plus 4 is 6. So it doesn't matter what you plug in. So that's how we investigate points of intersection with two lines. We set their parametric equations equal. This gives us a linear system with 3 equations, 2 unknowns. You pick 2 to solve. You solve the linear system, and then you see if it works in the second one. Here it did, and so we had a point of intersection. It might not always, so let's look at another example. All right. So in this example here, we have 2 lines, and I've given you a little note on your lesson sheet. It's always worthwhile just asking yourself, are these 2 lines parallel? If you can recognize they're parallel, it can often save you some work. So if you look at this question here, the first direction vector for line 1 is 2, 4, negative 3. And the direction vector for the second line is negative 4, negative 8, 6, which is actually negative 2 times m1. So these 2 lines are parallel. So we can already narrow it down. They're either parallel and never meet, or they're parallel and are the same line. Now, it's actually kind of hard to tell if these 2 lines are the same line, especially with lines in R3. So what we're going to do is we're going to investigate. So we're going to see, hey, I know 1, 1, 1 is a point on line 1. Is that also a point on line 2? Or I could do, I know 5 minus 9, 5 is a point on the second line. Is it on the first line as well? So I'm going to check that out. I'm going to ask, is 5 minus 9, 5 on line 1? If it is, then they're the same line because they're parallel and they'll share a point. If it's not, then they're parallel lines and they're distinct and they'll never meet. So I get to solving this equation. 5 minus 9, 5 equals 1, 1, 1 plus t times 2, 4 minus 3. So is there a value of t that makes this work? So I'm going to look at the x values. So 5 is going to be 1 plus 2t. I'm going to solve that equation. So I get 4 equals 2t. I get t equals 2. So I'm just going to stop there. So, t equals 2 is going to give me the 5 I need. So what do we get when we use t equals 2? So 1, 1, 1 plus 2 times 2, 4 minus 3. So we get 1 plus 2 is 5, as we expected. 1 plus 2 times 4, that's 8. 1 plus that is 9, positive 9. 1 plus 2 times negative 3, that's negative 5. So I get the 5 I need, but I don't get the y. I get a different point. So it turns out that 5 minus 9, 5 is not on L1. So we've just kind of solved this problem. We know they're parallel, but we know that a point on line 2 does not on line 1. So we've finished this off. They are parallel and distinct. No points of intersection. They never meet. So you should take note and just kind of have a look. And if you can notice that your lines are parallel, then you just have to do a bit of investigating to see if they're the same line. Now, if you had if you'd used the same method we did in our previous question, it You might ask, well, what would happen if I did that? So what happens when you try to solve a linear system where the lines never meet is at some point along the way, in our last example, we did the math, we got a t value, we got an s value. At some point along the way, your t's or your s's will cancel out, and you're going to get a statement like this, something like this. You're going to get like 0 equals 1 or something like that, a statement that is obviously not true. And if you're trying to solve a linear system and it gets down to something like this, then you know there's no solutions, so no POIs. But we can save us some work. In this case, we saw the lines were parallel. But keep this in the back of your mind. Like, I expect you guys today to recognize if lines are parallel and just go through this and not have to come to this. But at some point in the next couple of days, we will come to situations where there's just no way to tell. And we'll see that this kind of scenario pops up. Let's look at our third example. So here we can look at the direction vectors, and it's pretty obvious that these lines aren't parallel. So let's see what happens when we try to solve this linear system and see if there's an intersection. So I'm going to use our same method as before. Get the parametric equations, set them equal. So 2 plus t equals 3 plus s. 2 plus t equals -1 minus 2s. And 1 plus t equals 2 minus s. All right, I can actually already see some fishy things going on here. Let me just rearrange those. So I'm going to put, let's put s minus t, bring the 3 over, equals -1. That's equation 1. I'll bring the 2s to the left in this one. 2s plus t equals -3. Call that equation 2. And then finally, bring the s over. I get s plus t equals s plus t equals 2 minus 1, 1. And let's go about solving this guy. Now I'm looking at, I have lots of options. The s's match, elimination would be great. And the t's match in all three. So just to be different, I'm going to solve in this one. Systems 2 and 3, not because it's easiest, just to show you that you can do you just got to pick a pair and just solve. Last time we did 1 and 3, this time we'll do 2 and 3. And if I just subtract equation 2 minus equation 3, I eliminate the s's, or limit the t's, and I get s equals -3 subtract 1 is -4. S equals -4. And if I sub that into, looks like 3 is easy to solve that. Be careful here. At this point, we're solving the system 2 and 3. So I actually have to plug this into 2 or 3. I can't plug it into 1. So I got -4 plus t equals 1. So that would be t equals 5. And you can check it out yourself. Like for equation 2, 2 times -4 is -8, plus 5 is -3. Those things work. Let's check in 1. Those values for s and t definitely worked in 2 and 3. So let's check in 1. We get -4 subtract 5 equals -1. -9 does not equal -1. So in this case, we have no solutions. There's no value of s and t that works in all three. There's a value in s and t that makes the y and z values match up, but not the x value. So these are non-parallel lines, and they don't meet. These are skew lines. Now, earlier on, you may have been able to recognize a little shortcut here. I might just share with you now. Here we have 2 plus t equals 3 plus s, but 2 plus t also equals -1 minus 2s. So at that point, if you wanted to subtract the two equations right away, you'd get 0 equals, and this is for solving equations 1 and 2. You get 0 equals 4 plus 3s, and you could go on that way. There's just lots of options for you to solve linear systems. But for me personally, I like to rewrite them in the form that I'm used to from grade 10. Pick a pair, solve like we used to in grade 10, and then check in the last one. And it's an algorithm that just works every time. It's pretty easy to do. So yeah, -9 definitely does not equal -1. There's no solutions. These are skew lines. So this actually begs the question. So they're skew lines. They're going to pass each other, but how close do they get? What's the distance between those skew lines? So we're going to investigate that now. So the distance between two skew lines is, it depends on the point you use on each line. And if you think about it, these two lines kind of passing each other, depending on the points you choose, the distance between them is going to be different. Like here, these are two different points in the lines. P1 and P2 will have a distance between them. A and B will have a distance between them. So we say that the distance between skew lines is the shortest distance. So formally, when you're finding the distance between two lines, you're always finding the shortest distance. So we'll go with that. Back in grade 10, you guys actually learned how to find the shortest distance from a point to a line. And many people don't like doing it. But what happened in grade 9 was, if you had a point and a line, and the point is different distances away from the line depending on where you're talking about the line. But the shortest distance to the line, you learned in your grade 10 math course, is along a perpendicular. And it's the same idea here. The shortest distance between any two skew lines is along a line that's perpendicular to both. And we have a special word for that. It's along a normal. And we know that lines in R2 don't have a unique normal. They can point in any direction around the line. So line 2 has this set of normals around a line. Line 1 will all have its own set of normals, but there's actually going to be one normal that's shared between the two of them. So on this diagram here, this line from A to B, you can think about as a shared normal. And we know how to get normals, right? If we have two lines, each with their own direction vector, if you want to find a vector perpendicular to both, i.e. a shared normal, we can use the cross product. So the idea is here, that shortest distance is from A to B. So I'm just going to draw a dashed line that's parallel right here. And if we want to find that shortest distance, what we do is we project any 2 points in a line, like P1, P2, we project them onto the normal. And that gives us the shortest distance. So I'm going to call this D, the shortest distance. It is I'm going to be careful here, the projection onto N of P1, P2. This is the one time of year that I do this, so I got to be real careful. How do we get projections? Or it's the length of that vector projection. And so how do we get vector projections? We did the following. So we're projecting P1, P2 onto N. So that vector projection will be in the same direction as N. And if you recall, we had some dot products, and P1, P2 only appears in the top. So it was P1, P2 dot N over N dot N times N. So let's simplify this a little bit. This is a scalar, and this is a vector. I can simplify this as the absolute value of P1, P2 dotted with N Remember that n dotted with n is the magnitude, that's an n, squared. And then I can use my properties of vectors and just kind of take out the n with its magnitude. And so we have a factor of magnitude of n on the top and bottom. And this gives us a tidy formula that we can use to get the distance between two lines. It's given by this. The distance is the magnitude of P1, P2, dotted with n, over the magnitude of n. Sorry for squeezing it in there, but it's also on the previous page there. I might actually just write it bigger and neater. I suppose you could write it this way too. The absolute value of P1, P2 dotted with n over the magnitude of n. I actually like that better. If you're taking notes, use that. Yeah, I'm actually going to just erase that then. Yeah, I do like that better. Yeah, and it works out the same, but I think that's just a little tidier. So that's pretty cool to find the distance between two skew lines, how kind of easy it works out to do. All you need to do is calculate the shared normal using the cross product, and then you just need to know 2 points in the line, which you do. If you have the equation of both lines, you know a point on each line. So let's first find the shared normal. So I got to flip back because I don't have the, so my first line has a direction vector of 1, 2, 3. So that would be 2, 3, 1, 2. Second one is 2, minus 1, 1. So minus 1, 1, 2, minus 1. And now we'll do the cross product. We get 2, subtract negative 3, that's 5. 6, subtract 1, that's 5. Negative 1, subtract 4 is negative 5. Okay, so a shared normal is 5, 5, negative 5. I might suggest if 5, 5, minus 5 is the normal, then 1, 1, minus 1 is 2, because those are collinear. And just smaller numbers can make calculations a lot easier. So let's do this. D equals the magnitude of, so P1, P2. So let's get that. So this is P1 is 5, 4, 5, negative 4, negative 2. P2 is 2, 0, 1. So P1, P2 will be 2 take away 5, negative 3. 0 take away negative 4, that's positive 4. And 1 take away negative 2 is positive 3. Dotted with my normal, 1, 1, minus 1, over the magnitude of my normal, which is, it's easy to find, 1 squared plus 1 squared plus negative 1 squared. So on top, we get the magnitude of negative 3, or the size of, the absolute value of negative 3 plus 4 minus 3 over the root of 3. So that's negative 6 plus 4, negative 2. Absolute value is 2. We get 2 over root 3 units. The shortest distance between those two lines, 2 over root 3 units. So this idea of shared normals and this projection of 2 points onto the normal can be a little trap your minds around. So that might take a bit to digest, but the formula is easy. All you need is direction vectors to get a shared normal, and then 2 points in the line. You can find the distance between any two skew lines, i.e. the shortest distance. All right, that's it for today. That was enjoyable. I had fun doing that. I've given you guys some practice to work on, posted on Brightspace. I hope you guys have a great day, and we'll see you soon.